So now we know capacitors are very common circuit devices. When we look at a circuit, we see that there are lots and lots of capacitors in our circuit, and this is really common. Most circuits do have multiple capacitors, which means they need to be connected in our circuits. So the question is, how do we connect or combine capacitors? And when we do connect them and combine them, how do we treat them? How do we deal with them? So we're going to talk about two kinds of connections first. First is series, and then we'll talk about parallel, and then after that we'll do the combination. So we're going to start with series. So a series combination is probably the most straightforward combination. So what happens is we take a wire, we connect it to one end of the battery, and we take our ideal wire and we connect it to the first capacitor. And we come out of the first capacitor, straight in the second one, straight out of the second, into the third, out of the third, and back into the battery. The capacitors are all joined end to end, they're all in a row, and there's no branches in between them. Okay, so it all goes straight in a line, straight in a row. What happens in a circuit like this, so once it's all connected, like we talked about when we said about charging a capacitor, what happens is that the chemical reaction inside the battery makes a positive charge move from the negative towards the positive. The positive charge comes out of the positive terminal, goes around the circuit, through the ideal wire, comes down and hits the plate. Positive charge gets dropped on the top of this plate, which repels a positive charge from the bottom plate. That keeps flowing. Because a positive charge is repelled, that leaves this one to have a negative behind. The positive that's repelled hits the top of this plate, repelling a positive from this plate. That's left with a negative. The positive repelled off that one hits this plate and has to stop. That repels a positive for this one, leaves it negative, comes back around the circuit, and so on. So every charge that leaves the battery, for every single charge that leaves here, one charge gets deposited on the plate. It happens over and over and over, and we get the same amount of charge left on every single capacitor. So we get plus Q on the top plate, minus Q on the bottom. That happens for every single capacitor. So this is what we know about capacitors in series, is that every single capacitor connected in series will carry the same charge. So every capacitor has same charge. So series means same charge. So we could say Q1 equals Q, Q2 equals Q, Q3 equals Q. Okay, what next? So, because there is a charge on the two plates of the capacitor, they're separated by a small distance, there will be a potential difference between the plates of the capacitor. So capacitor C1 will have a potential difference delta V1. Capacitor C2 will have a potential difference delta V2. Capacitor C3 will have a potential difference V3. Okay, now let's think about what do we know about the potentials. The battery supplies potential. It has a total amount to put into the circuit, and that total amount has to get divided over the three capacitors. What does that mean in terms of an equation? So battery supplies potential and that net potential has to be split or divided over all the capacitors. What that means is that the net potential supplied, delta V, is the sum of these three potentials, delta V1 plus delta V2 plus delta V3. Okay, so however much potential we put in has to be split somehow over the three capacitors. Well, if we remember our equation for capacitance, we know that C is charge Q divided by delta V. That means that delta V must be our charge divided by our capacitance C. Let's fill that in right here. Delta V1 is Q1, which is just Q divided by C1. Delta V2 is Q2, which is just Q, divided by C2, plus delta V3, which is Q3, which is just Q, divided by C3. Okay, so the net potential is split. We know delta V is Q over C, so this is a way to write down the net potential. Okay, what can we do next? So something we can do, and something we actually do, is we create what's called an equivalent circuit. What we mean by an equivalent circuit is we remove capacitors C1, C2, and C3. We take those three out. We put one single capacitor in its place, and this single capacitor gives the same behavior as these three when they're in separately. And what we mean by the same behavior is that if we have the same size battery, then we get the same size charge. Okay, so that's what an equivalent circuit is. We put in an equivalent capacitance that will carry the same charge as these three when it's connected to the same battery. So that's what we mean by equivalent circuit. So let's draw a connection. Here's our equivalent circuit. An equivalent circuit means we replace C1, C2, and C3 by C equivalent, so EQ for equivalent, so that C equivalent has charge Q when connected to battery with potential delta V. So this equivalent capacitor here has charge Q on the plates, it's got delta V between the plates, and we know from our relationship that the capacitance CEQ will be the charge divided by the potential. Okay, so this is interesting. So that means that delta V will be Q divided by C equivalent. So I'll take this equation and I'll rearrange it for delta V. And I'm going to pop that in over here. So delta V is Q over C equivalent. Looking at this equation now, I've got Q in the numerator on both sides, so I can divide through by Q, and I get a final result which tells me my equivalent capacitance in terms of my individual capacitors. 1 over C equivalent is 1 over C1 plus 1 over C2 plus 1 over C3, and if we had more capacitors, we would just keep adding them. Okay, so this is the expression to find equivalent capacitance for a set of capacitors connected in series. If you did physics in high school, you might recognize this formula as being similar to the formula for resistors in parallel. So if you did physics in high school, just watch out that you don't get these equations mixed up. Okay, let's do an application. So what's something we use series capacitors for? And one neat application is actually your cell phone, your touch screen on your cell phone. So I'm not sure if you've ever thought about how that works. So here's your cell phone. You've got a glass on top. And what happens is that above the mechanics of your cell phone, there are actually parallel layers of perpendicular strips. So inside the glass, there's a set of strips that go like this, and there's a set of strips that go like this. They're perpendicular to each other. Every place where these transparent strips cross is a capacitor. So then, we've got these strips underneath the glass in your phone. When you touch the top, so when you touch the glass, it's adding a second capacitor, your finger in the glass. It's adding a second capacitor to the capacitor, which is these cross strips. The circuits inside your phone can detect that change in capacitance because we've now got two capacitors in series. It can detect the change in capacitance, so it knows where you touched because there's a change in capacitance.